potential for lesion stuff.
Yeah, good point.
Cool. So everyone can see the PowerPoint screen.
So last one of Tommy's.
Okay, sweet. So tonight we'll be taking a look at resonance and power factor. So we'll continue on from what we did last week, talking about reactance in the AC theory, and we'll start to develop our idea of what resonance is and how we can affect power factor. Cool. So first, a little bit of revision. So before we move into the new topic, we'll revisit some of the key ideas that we talked about last week. So remember, the balance between inductive and capacitive reactance is what leads us to resonance, like we started to talk about. So let's confirm we still understand how the reactance and impedance work before we look at how they cancel out. So what happens to current when inductive reactance increases in an AC circuit? So we have our circuit, and all of a sudden we've increased the inductive reactance. So all of a sudden the inductance has risen. What happens to the current? Yeah, it lags. So that's, if we have an inductive circuit, it definitely lags. But something else changes. What could that be? Yep, so we have a lag behind the voltage. We have current opposition. But because we've increased our inductance and increased our reactance, yep, the current should decrease because as the inductive reactance increases, we have more opposition to the current changing. So we have more opposition to the changing current. So therefore, we will have less current as we increase our inductance. Cool. So what does the ratio RZ represent in an AC circuit? So as a ratio, what does RZ represent in an AC circuit? Remember, R is our resistance and Z is our impedance. Yes, so it is the resistance divided by the impedance, and this represents the power factor or cosine theta. It's a measure of how much the current is doing useful work. So lower value means a more reactive circuit. So we're using more power to overcome that reactive nature in the circuit. Cool. So when XL and XC equals XC, so our inductive and capacitive reactance are equal, what happens to the total reactance? Yep. So the total reactance becomes zero because the inductive and capacitive reactances cancelled each other out. So the circuit then behaves as if it only has resistance. So it behaves as a purely resistive circuit. Cool. So what does it mean when current and voltage are in phase? Yep, so we have resonance, current and voltage rise and fall at the same time. Yep, purely resistive circuit, phase angle of zero. Yep, so it basically, yeah, means we have a purely resistive circuit. If we were shown a graph with phase and voltage, sorry, voltage and current being in phase, we would know that circuit is purely resistive. And so all of the power supplied is converted into useful work. So no reactive energy stored. So that's enough about last week. So we'll move into resonance. And before we keep going, I will just let you guys know that if anyone's watching this afterwards, everyone got marked present yesterday because of the fact that we moved the class at the last minute. Cool. So we've seen that capacitors and inductors both store energy, just in different ways. The capacitor stores it in an electric field, resisting that sudden change in voltage, whereas an inductor stores the energy in a magnetic field, resisting sudden changes in current. If we put both in the same circuit, we get some interesting things happening. The capacitor discharges and pushes current into the circuit that builds the inductor's magnetic field, and as the inductor's field collapses, it pushes current back, recharging the capacitor. This back and forth flow of energy can continue in a rhythm, a bit like a child swinging, gaining height when you push at just the right moment, or when we bounce on a trampoline and we bounce at just the right time and we get an even bigger boost. Or have anyone seen the experiments where they bob a ball up and down in a trough of water and they eventually hit a resonance frequency? So when the rate of energy exchange between the inductor and the capacitor is perfectly matched, we reach this condition called resonance. So it can be useful, but it can also cause us a lot of problems. So in radio communication system, we use resonance to deliberately tune into specific frequencies, selecting one signal while rejecting all the others. But in power systems or poorly designed circuits, unwanted resonance can cause excessive current, voltage spikes, and even component failure. So understanding resonance helps us design safer, more efficient systems and avoid destructive situations. So we can use it for good in certain situations, but if we have it in our power systems, it can cause extreme hazards. So does anyone need me to go back to the previous slide, or are we all good to carry on further? Okay, cool. So we'll move on. So then we move on to look at the energy exchange concept. So the capacitor's electric field and the inductor's magnetic field will continuously trade energy. So they'll keep supplying each other with power. And as the magnetic field builds up even more and the capacitor charges up even more, it will build and build and build. When they are in perfect sync, it's at its maximum efficiency and resonance occurs. So it is very rare that it happens out there by accident in the wild, but it can happen depending on how the state of the inductors and the state of capacitors. If for some reason we had a slightly more inductive circuit, then all of a sudden the magnetic field is lessened for some reason. Maybe there's a slightly increased resistance in the windings of the inductor, and therefore we get less magnetic field buildup, and it gets to the point where we get a perfect match and we get resonance. So we can usually design the power system so that doesn't happen, but there is a risk of it happening out in the wild. Cool. So conditions for resonance. So we would have to have an inductive and capacitive reactance in an equal magnitude, but opposite in phase. So we would state that XL has equaled XC. That means the total opposition to current flow is therefore purely resistive. And depending on the circuit, that means that we could get quite a low resistance if we were using the reactance to counteract current flow. So at resonance, the impedance is minimum or equal to the circuit resistance only. So we've lowered our impedance level to the purely resistive level of the circuit. And all of a sudden that current is maximum and in phase with the voltage. We get an energy oscillation between the inductor and a capacitor or the capacitive element. And we get that back and forth that we were talking about where energy constantly builds up and up and up and up. What this means in reality, beneficial, it can be used to tune circuits, filters, and oscillators. So we can use it for tuning in radio circuits or electronics. But harmful, we can cause over voltage or over current conditions in the supply network with transformers or long cable runs. So again, if we imagine the playground swing, each push at the right time adds energy and the swing goes higher and higher. Resonance is the electrical equivalent. If the timing is right, energy will build efficiently. But if the swing is pushed too hard or left uncontrolled, it can go too high, just like current or voltage rising dangerously in our electrical circuit. Has anyone heard of the break step bridge? Oh, I guess you call it a myth, but it is technically a theory. The break step bridge. Okay, so the break step bridge was a myth or a theory that came about for basically people marching across bridges. Yes, exactly, Jordan. That's where I was going with this. So in Mythbusters, they tested if a group of basically armed forces members walking in sync across a bridge would have enough of a resonance or oscillating effect to destroy a bridge. But everyone's seen the trick where vocalists will smash glasses with their voices. See the opera singers singing really high, and then all of a sudden the glass shatters. So that's resonance as well. Basically, they're matching the frequency of the glass with their voice, causing it to resonate, oscillate, and then shatter. So we convert the sound waves to electrical current and the glass to our circuit. That's potentially what can happen when we have resonance, especially in an uncontrolled manner. Cool. So to summarize what we've gone over so far, it's resonance is when inductive and capacitive effects cancel each other. It occurs when energy is exchanged at the same rate between the components. So the circuit's opposition drops to resistance only, and our current peaks. We can have useful for tuning circuits or harmful, causing overvoltage and overheating. There's a lot of well, they used not I don't know so much anymore, but there used to be a lot of money to be made out of knowing how to perfectly tune an electrical circuit to get the almost close to resonance, but not quite resonance to create almost perfect power factor. But obviously, it's quite dangerous to get to almost perfect power factor. Cool. So now we'll talk about the frequency and circuit behavior. So we understand resonance as an energy exchange between the inductor and capacitor. So let's look at what happens in real AC circuits as the frequency changes. Cool. So as we raise the supply frequency, the inductor's reactance, that being XL equals 2 pi FL, increases, while the capacitor's reactance, XC equals 1 over 2 pi FC, it will decrease. And we at one special frequency, these two reactances are equal, and that's the resonant frequency, written it as FR equals 1 over 2 pi square root LC. So this is what we're looking for when we're using resonance to tune out certain frequencies. We can use inductors and capacitors at very precise ratings to cancel out certain frequency when we're doing radio tuning. Cool. So frequency versus reactance. So when we have below resonance, so below that horizontal line, our capacitance is greater than our inductance. So it behaves capacitive and the current leads the voltage. So we look at the horizontal line of our power factor triangles when we draw them as our resonance line. So our resistance line is considered the same as our resonance line. So at resonance, we have XL equals XC, and the circuit is resistive, and the current and voltage are in phase. And then when we are above resonance, we've swapped XL and XC, so XL is bigger. So our circuit behaves inductively, and our current lags the voltage. So always remember that resistance line is also considered our resonance line. So we don't ever want our hypotenuse or our impedance to touch our resonance line if we are in AC and if we have inductive or capacitive components. Remember, it's only if we have inductive and capacitive components that we have to worry about resonance. If we only have a purely resistive load, for example, a heating element, then that's all we need to worry about, and we don't need to worry about resonance too much. But obviously, the supply network has a lot of inductive components to it because of the fact that we need to use transformers to step up and step down the voltage throughout the network. Cool. So our current and impedance at resonance. So we consider impedance to be at its minimum or equal to the resistance R. Current is maximum, so I equals V divided by Z. So if we have a minimum impedance, we have a higher current. Any further increases in frequency makes the circuit inductive again, and current falls. So if we increase the frequency, we get inductive. If we decrease the frequency, we get capacitive. But it's usually that we increase the frequency. Cool. So we'll take a look at a circuit behavior graph. So as we get towards resonance, our current all of a sudden spikes because our impedance has dropped off extremely. So at the golden frequency, we get an increased current because we have eliminated our impedance. But as we go to a lower frequency, capacitive reactance increases. So we get a capacitive impedance, and then the opposite if we increase frequency. So is this making sense to everyone, or do I need to go over something again? I'll try and make it not such a long night as we usually do because it is an off night. So we'll move to the next part. Cool. So this is what resonance would look like in a real circuit. So you can see that as the inductor and capacitor swap energy faster and faster, the voltage across each component starts to rise sharply. So even though the supply is small, the local voltages in the circuit can spike dangerously, as shown here over 11 kV in the simulation. This is why resonance can be a double-edged sword. We can use it deliberately in tuning circuits, but it can also destroy components if it appears unexpectedly in a power system. So this circuit was tuned perfectly in terms of the size of the capacitor and inductor to create this. So normally you would not get exactly 201 millihenries or 507 microfarad, 50.7 microfarads. But yeah, if we don't control the voltage properly, we can cause massive voltage spikes. Cool. So the high energy doesn't come from the supply, it's created by reactive energy exchange. In a resonance circuit, voltage across each reactive element can be much greater than the applied voltage. So because of that back and forth of the resonance, we can all of a sudden have an increase in the applied voltage. Volts total circuit current, however, is limited by the resistance. So our current is limited, but our voltage is not. So it highlights the importance of proper circuit damping or resistance to avoid uncontrolled resonance. So where might resonance like this occur accidentally in real installations? So where do you think you'd be might have this occur in a real installation? Motors, yeah. Anyone think of anything else? What about some residential applications? Anyone think of any residential applications that might accidentally cause resonance? Yep, AC to DC conversion. So where might that be happening inside a residential? Yep, lights, downlights. Yep, solar panels. Yeah, and the drivers for the lights. Yep. Yep, chargers, laptop chargers, phone chargers. Yep. So yeah, these are all possible places where you might get accidental resonance. Cool. So we've seen that resonance isn't just a textbook idea. It occurs when inductive and capacitive reactances balance. So at resonance, we have XL equals XC, Z equals R, the minimum possible impedance. Our current goes to its maximum, and voltage and current are in phase. So below frequency is capacitive. Resonance frequency is capacitive. Above it is inductive. So the shape of the current frequency curve shows how strong the resonance is. So it can show up in real electrical systems, often where we don't want it. Anytime an installation contains long cable runs, power factor correction capacitors, or transformers and motor windings, you've got inductance and capacitance present together. If their reactances happen to balance at some frequency, you can end up with resonant conditions, sometimes causing large circulating currents or damaging voltage spikes. So we do have intentional resonance, which is used for tuning circuits. I have not seen, well, the thing is you don't know if it's resonance or not until you actually, like, something goes horribly wrong. I have not seen first-hand evidence of resonance, but at the same time, there's a reason we limit our cable runs to the lengths we do without upsizing the cable. There's a reason we have capacitors. I think guys who are industrial, and I mostly did commercial residential, would probably see it more, especially where they have to use power factor correcting capacitor banks. I have seen plenty of transformer fires online that possibly could have been due to resonance because the guys who work on the network, there are power factor correcting capacitors inside of the transformers, I believe, or on the outputs or inputs of the transformer. Yeah, thankfully I've gone most of my electrical career without seeing too many dangerous situations like resonance or any fires or anything like that. Most of the time I've seen the aftermath of someone doing something stupid. Like when one of the builders tried to use a Makita battery and some 1.5 mil cable to jumpstart his car in the morning. Yeah, so the whole point we'll talk about when we get into power factor a little bit later in this lesson. We'll talk about the power factor and capacitors and exactly what we're trying to achieve there. So intentional uses, so yeah, tuning circuits, radio filters, metal detectors, designed and controlled. So these are designed and controlled uses of resonance, and they're usually in low voltage AC or DC circuits. So this is the good, useful resonance. Then we've got unintentional. So it's mostly in power systems, particular with capacitor banks and motor circuits. So in a big industrial factory where they use capacitor banks as power factor correction. So it can lead to excessive voltage on equipment. So all of a sudden, equipment that's designed to run at 230 or 400 is seeing 6, 8, 900 volts at the terminals. It leads to overheating and failure of the capacitors and transformers. And it can cause nuisance tripping of protective devices. So sometimes it's not necessarily the fact that there is leakage current for RCDs, but it can also be caused by some resonance, but it's more than likely leakage current. Cool. So we can use some methods to control frequency. So avoiding combinations of inductive and capacitive components at matching frequencies. And we follow the installation guidance of ASNZS 3000 and manufacturer's data. So we check to see at what frequency the capacitive and inductive components would reach a certain value of reactance, and then we make sure we don't use them in a way that on the matching frequency they would match in that way. So if resonance can occur at any time, we have inductance and capacitance. What sort of circuits in a typical building or plant might experience it? So can occur at any time, but what kind of circuits do you think it would typically affect? Talked about a couple of them, but what kind of circuits? Yeah, that's more of a kind of appliance. What kind of AC circuits? Think along the terms of industrial commercial. Yep, motor circuit control or just motors in general would have, especially single phase when we've got the capacitors. Then we've got any other ideas? Not even just the older ones. Modern UPSs use capacitors as well. And they do have a kind of step up, step down transformer in them to drop the voltage down for the battery. So yeah, definitely UPS, especially because it's got the smoothing capacitor on the DC side as well. Okay, so I don't know if many of you guys will have played around with it, but has anyone taken apart any fluorescent lighting circuits before, or taken apart fluoro light fittings? Yeah, so inside of the fluoro light fittings, they have power factor correction capacitors that are normally connected across the phase neutral supply, and they have a inductor called a choke, which limits the current spikes. So they have an inductor and a capacitor in them. So there is a chance of a resonant frequency there, as well as variable frequency drives. So if we're using the variable frequency drive and we accidentally set the motor control frequency to the wrong one, and the inductor inside the motor and the power factor correction capacitor interact in the wrong way, or if it's a single phase cap start cap run motor, um, then there's a chance of the varying frequency. We get it just the wrong one when we're adjusting the speed, creating that resonant frequency. So yeah, so power factor correction systems, because well, they're usually used to control inductive reactance, and so there's a lot of capacitors, and are long underground cable networks because the cables are can act as a capacitor or an inductor depending on how they've been run. So these are all things we need to be aware of when we are designing and building the circuits that we use. So now that we've talked about that, we'll move into the next part where we'll talk about true, reactive, and apparent power. So we'll get into the heart of what power really means in AC. So in DC, power is easy. Voltage and current are multiplied directly because they're always in phase. But in AC, the phase shift we saw when we talked about impedance changes the picture completely. Some of the current is doing useful work, while some is just moving energy back and forth between magnetic and electric fields. So we have three forms of power. Can anyone take a guess at what those three forms are? If anyone's read ahead in the materials, some of you guys may have already come across these three. Yep. So we have not active, but we call it true. So most of the time we call it true. It is sometimes referred to as active, but it is called true power, reactive power, and apparent power. So we have true power, or P, which is measured in watts. So it's that power that actually performs work. So it turns motors, produces heat, light, motion. Then we get reactive power, or Q. It's measured in volt amps reactive. So it's the power that oscillates between the source and the reactive components. So our inductors, our capacitors, and it stores and releases that energy, but does no net work. It doesn't actually do anything useful with that reactive power. And then the apparent power, or S, which is measured in volt amps. It's the product of the RMS voltage and current. It's the total effort the source must deliver to supply both P and Q. So take a moment to get these down. So when we're talking about true power, it's what's the power that's flowing in a resistive, and it's the actual measure of work done. So when we talk about power in terms of watts, it's the actual work done. It's how many joules per second of energy that we're using to do the work. And the reason we measure apparent power in volt amps is because it's the total voltage and current measured. So it's the total power supplied. It's why we usually rate transformers in kVA or VA, is because it is the total effort that the transformer can supply. Because we cannot guarantee what the power factor or the reactive power of the load we're supplying with that transformer is actually going to use. So therefore we measure our transformer in VA. It's the same with our motors. Our motors are rated in power, as in the actual power it can deliver through the shaft, but it's when we actually measure the current going into the motor, or we say that is the apparent power, or VA, that it is using. Does that make sense to everyone? Right. Is anyone still copying the points down, or shall we move on to the next part? Yep, all good, Connor. So it notes there the product of the RMS voltage. So it's the actual root mean square voltage, like we've talked about in previous lessons, not the peak voltage of 325. Sweet. So, like we've talked about previously, the beer analogy. So think of ordering a pint of beer. So the beer itself is the true power, the useful stuff you actually drink. The foam on top is our reactive power. It takes up space, but it does not quench our thirst. The entire glass, beer plus foam, is the apparent power. It's what the bartender has to pour. Perfect pour, no foam means a power factor of 1. A foamy pint means wasted space, a lower power factor. The goal is always to keep the foam to a minimum. But remember, we don't want a completely foamless beer, because we drink the beer through the foam, and we cannot get away from the foam because of the fact that it is a carbonated drink. So it is the cost of doing business. Yes, it is technically wasted, but it is the cost of doing business, and some of that foam does eventually collapse and turn into beer. So yeah, this is the way to remember it. So the kVAR or kilovolt amps reactive is the head or foam of the beer. The real power or kilowatts is the actual drinkable liquid, usable electricity. And then kVA is the total effort to pour that beer or the total volume of the glass. Cool. So linking it back to impedance, we have this. So cosine theta equals R divided by Z. So our power factor is equal to P over S, or our power divided by our apparent power, which is our hypotenuse, and which is equal to cosine theta. So our resistance is our power, our impedance is our apparent power. So the more resistive the circuit, larger R compared to Z, the more efficient it becomes. The more reactive the circuit, larger X, means poorer power factor. So the more impedance versus resistance, the worse the power factor. Cool. So power can be rationalized into a triangle much the same way impedance can. In fact, the two triangles are proportional to each other. Cool. So the adjacent side is the resistance. This represents the physical opposition to the current flow. It can be likened to true power, the power that actually does the useful work. So our horizontal line, resistance and true power, go hand in hand and they are proportional. The same is true for our opposite side, or the upstanding side or downstanding, depending on the way the power factor is going. It's our reactance, or X. It represents the opposition to changes in current by our inductors and our capacitors. It's also our reactive power side, or our Q. It is the energy absorbed and released in creating the magnetic field or the electrostatic field. It's often called wattless power, as it doesn't contribute to the real work. Cool. Then we have the hypotenuse, or the impedance, Z. This represents the total opposition to current flow in the circuit. It can be likened to our apparent power, the total energy supplied to the circuit, so not used by the circuit, but supplied to the circuit, including both the useful and useless components. Even though the useful output power may be less than the total value, we must always size the cables, fittings, and protective devices for the apparent power, as it represents the full demand placed on the system. So if our apparent power is 2,000 watts, but our usable power is only 1,500, we need to plan our cable runs, our cable sizes, and our protective devices for the apparent power, because that's the actual power that's going to be flowing through the circuit. And the reason we don't add them together and we use the triangle is because that magnetizing, demagnetizing, or building up the charge and then the charge being put out, it's still technically being used by the normal power, but it's not a case of just adding them together, which is why we have to use them as a vector summary. Cool. So we'll have a look at an actual numerical example. So we have a single phase AC circuit with the following values. So our supply voltage is 230 volts. We have a current of 5 amps, an impedance of 46 ohms, and a resistance of 36.8. So quickly write those numbers down, and then we'll move into the actual calculation side of things. So, step one, we need to determine our power factor. So, the ratio of resistance to impedance gives us our power factor. So, if you've written down the values, have a go at trying to figure out what our power factor will be. So based on those numbers, what's our power factor going to be? Do everyone else agree? Okay. Cool. So our formula will look like this. So our cosine theta would be equal to our resistance divided by our impedance. So 36.8 divided by 46, giving us a 0.8 power factor. So the power factor would be 0.8 lagging since the circuit is inductance. Cool. So then we're going to have step two. We're going to calculate the active or real power. So have a go at figuring out the active or the real power. So yep, single phase. Yep, 5 amps. Cool. Only one guess. Okay. So yeah, we would have, so our power equals volts times amps times our power factor, because we're only dealing with our active or our real power. So 230 times 5 times 0.8, which gives us 920 watts. So this is the portion of power actually converted into useful work, whether that be heat, motion, etc. Cool. Then we have step 3. We need to calculate our apparent power. So have a go at calculating what our apparent power is. Have a go at calculating what our apparent power should be. So we can just take our voltage times our current, 230 times 5, 1150 VA. We could also multiply, or sorry, we could divide our true power by our power factor. So we could have divided 920 by 0.8 and we would have gotten 1150 watts or 1150 VA. Remember, when we're talking about apparent power, it's in VA. It's the power actually supplied to the circuit. So we need to get used to that, guys. When we're talking about true power, we're in watts. When we're talking about apparent power, we're in VA. And when we're talking about reactive power, it's VAR or volt amps reactive. Remember, watts is the rate at which work is done, whereas VA is the total voltage and current supplied to the circuit. So once we've figured that out, we need to figure out, so show the relation, so we need to, now that we have P and S, we can show how they're related through Pythagoras. So S squared equals P squared plus Q squared. We can then rearrange or transpose this to find our reactive power Q if needed. So Q equals S squared minus P squared. So we substitute our values. Q equals 1150 squared minus 920 squared, which gives us 690 volt amps reactive. So that's the total measure of our reactive power. Remember, a lot of the times in the electrical industry, everything comes back to our right angle triangle. Cool. So now we can go and then link it all together. So this is our beer glass in numbers. 920 watts of beer, 690 volt amps reactive of foam, and a total glass of 1150 volt amps. So once we have all of those values, we can then put it into a table and figure it all out. Sometimes it's even easier. Probably seems like a waste of time at first, but when you're doing questions that involve active, reactive, and apparent power and power factor, to write it all down into a table like this, so that way you can figure out what's what. Just fill in the missing values in the table. Cool. While you guys get that down, does anyone have any questions about anything we've covered so far? Yeah, we always need to remember when we're doing active power, it's watts. It's the actual work being done. Whereas reactive power is our volt amps reactive, the total voltage and current being used up by the reactive component. And our VA or our volt amps is our apparent power, which is the total power that is being sent to our load. It is also what we are usually being billed for when it comes to power. So does anyone need more time to write that down, or shall we move on? Cool, sweet. Not so much efficiency, it is power factor. Efficiency relates more to things like losses. So when for a motor, we have losses in the terms of what we call windage or friction. So that would be something about efficiency. Whereas our transformer, our efficiency would be losses in the windings when we talk about our copper losses or our hysteresis losses, iron losses, sorry. So that's more to do with efficiency. So when we do look at stuff in year three, we will be taking into account efficiency and the power factor. So in year three, you will get questions about transformers that include both losses and the power factor of the load, as well as sometimes the power factor of the transformer itself. Cool. You good, Connor? Cool. Sweet. So now we'll look at what it really means. So power factor is a relationship. It's a cosine of the angle of the triangle, phase angle. It's the uh, resistance divided by our impedance, and it's the um, true power divided by the apparent power. It is a ratio. So when we get that 0.8, that is actually a ratio. It's the ratio that's given to us by cosine. It shows the efficiency of the current, not the efficiency of the load, of the current. How much of it contributes to real work rather than simply moving energy back and forth. A power factor of 1 means all the current is productive, so a purely resistive load. A power factor less than 1 means some current is reactive, whether that's lagging or leading. So, so why the voltage and phase matters. So when voltage and current are in phase, every amp and volt combine perfectly to produce the power. When they are out of phase, part of the current is wasted in the back and forth energy exchange between the magnetic and electric fields. The greater the angle, the smaller the useful or real portion of the power triangle. So you can see that everything ties together. The power factor connects resistance to impedance, and that same ratio shows up in the power triangle. When we know any two sides of the triangle, whether impedance or power, we can always find the third. Or if we have one side and the angle, we can figure out the other two using SOHCAHTOA and TOA. This is what makes AC power analysis so powerful. It's all the same geometry we've been using since we talked about resistance and reactance, and all the way back to high school when we were doing year one, NCA level one maths. Cool. so now we'll look at visualizing and correcting power factor. So we'll build a power diagram to see what poor and corrected power factor looks like in real numbers. So we'll start with an inductive load, then we'll add a capacitor to compensate it. Cool. So this is a power factor triangle. So this is our first one. So we have our active power P in the bottom. We have our reactive power Q in VAR on the right. And we have our apparent power, so our S in VA. So this triangle is obviously quite inductive because it is above our resonant or our power line. So we have a power of 900 watts. We have a Q of plus 600 VAR, so inductive. So to figure out our VA, we take our P squared plus Q squared and we square root that. That shouldn't say, 900 squared plus 600 squared, which gives us 1080 VA. Then we can figure out our power factor angle. Cool. The angle is cosine to the negative P over S. So 900, 1080, 33.56 degrees, which gives us a power factor of 0.83 lagging. So this 34-ish degree phase angle shows our current as lagging the voltage, a lagging power factor of 0.83. The supply must provide 1080 VA of apparent power, even though we're only getting 900 watts worth of usable work out of it. The rest, 600 VAR, is reactive power bouncing between the supply and the magnetic fields in the load. So power companies charge us for the apparent power because they still have to supply the current that supports that. All good, Jack. Everyone's been marked present for yesterday's night class anyway. Just the video will be up pretty much as soon as I'm finished the class. We're almost at the end. Cool. So now we can look at correcting it. So we still have our active power, our reactive, and our apparent. Our power is still 900 watts. But what we're going to do is we're going to take 450 VAR of capacitive inductance and add it to Q, or our capacitive VAR. So Q net is 600 minus 450, which gives us 150 VAR, which changes where our apparent power or our hypotenuse goes. So now we redraw that, and this is our new apparent power. So, and this would be our new angle. So our triangle now looks like this. It's a much squatter triangle, which means we're going to have a better apparent power and power factor. So our apparent power in this, so it should be S2 equals the square root of P squared plus our Q net, or our reactive net power. So 900 squared plus 150 squared square rooted gives us 912 VA. Cool. So we can then figure out our phase angle, giving us 9.4 degrees, which gives us a power factor of 0.98657, or rounding out to 0.99 lagging. So a lot better and very close to resonance, but not quite there. So by adding the capacitor, we've reduced reactive power from 600 VAR to 150 VAR. The apparent power fell from 1080 to 912, a 16% reduction in total current draw for the same useful power output. In real installations, this is what capacitor banks do. They inject capacitive VARs to offset inductive VARs for motors and transformers. The result is a smaller phase angle, higher power factor, cooler cables, and lower energy costs. So there is a lot of money to be made in power factor correction because companies will pay big bucks for you to come in and fix their power factor because it will save them literally thousands on their power bill. Some companies don't care, but for the majority, they will pay through the nose to have better power bills. So, yeah, there is quite a bit of danger in these capacitor banks, though, as they click in and out because they hold a lot of charge. So when they're clicked out, if they're not fitted with a proper discharge path, they can sit there holding their charge for months. There's been reports of people coming across capacitors that have been disconnected and sitting on a shelf, and they've tested them for voltage, and they've still held the charge after several years. So it's always good to be careful around capacitors, especially the power factor correcting ones, because they're usually quite big capacitors. Cool. So some key points to take away from what we just talked about. So before we had a Q of plus 600 VAR. We had a power of 1080 VA, a phase angle of 34 degrees, power factor of 0.83 lagging, and we had high current and losses. After the correction, we had 150 VAR net, a apparent power of 912, angle of 9.4 degrees, so small angle, 0.99 lagging power factor, and we have lowered our current and improved our efficiency. So this is why we add capacitors to correct power factor, because it means we get reduced energy bills. The opposite is also true. If our power factor is too capacitive, then we need to add inductors into the mix to change things up. Back in the early days, when they first started turning on a lot of the LED lights in these big apartment buildings in Wellington, they all of a sudden had a power factor going the other way, and they weren't sure how to fix it. So there's actually a few apartment buildings in Wellington where they had to install giant kind of radiant heaters or inductive boiler tanks to compensate for the power factor going the wrong way. It's quite a bit of an issue quite early on, but that was a few years ago now. Cool. So remember, our reactive power inflates the total current draw from the supply and increases our energy bill. Our apparent power determines the current rating for our cables, our transformers, and our switchgear. Even if our load is only 2 kilowatts, if we have an apparent power of 3000 VA, we need to plan for the 3000 VA, not the 2000 kilowatts. Capacitors supply an equal and opposite reactive current, which will cancel out the inductive effect. The smaller the remaining Q, the shorter the S vector or our apparent power vector, and the smaller the phase angle, which means a better power factor. Is this making sense to everyone, or do I need to go over anything again? If anything's not making sense, this is the best time to ask. It is mostly math, one thing affects the other, and then it changes the math. It changes the numbers, and we recalculate. So once we know the VAR that we need to achieve, we can then figure out the capacitive reactance that we need to do to achieve that? Is we can figure out what the resistance of our wattage is, and then we can use the power factor. Yeah, we can use the power factor angle to change things. We will talk about that a little bit later and go into a bit more detail on how to calculate the amount of reactance we need and how to achieve that. Cool. So a bit of summary and recap. So let's take a few minutes to summarize what we've talked about today. We explored how inductors and capacitors affect the phase angle, how that phase angle defines power factor, and how apparent power represents the total demand on the system. Then we saw how adding a capacitive element can help counteract the inductive effects, improving the power factor and reducing current draw. The same would be true if we had too much capacitive reactance. Cool. So reactive power Q, it does no useful work, but it does affect how much current the supply must provide. Our apparent power S is the total current demand and what we pay for. It includes both active and reactive components. Our power factor shows how efficiently power is used. So lagging, inductive, leading, capacitive, unity, PF equals 1 is fully resistive. So power factor correction adds capacitance or inductance to offset inductive or capacitive reactance, balancing the circuit and improving efficiency. So we had too much inductance, we add capacitance. If we have too much capacitance, we add inductance to a point. We don't want to take it too far that we either get resonance or we throw it even further back the other way. Cool. So we'll just finish off with a few questions and then we will call it a night. So, what causes poor power factor in an inductive load? So, what about the inductive load causes the poor power factor? Yep, not quite what we're looking for. Yes, too much reactive power, but what causes the reactance? Yeah, current lags the voltage. Yes, there is a phase lag. There is one more element that we're looking to add to that. So think about what a inductor has versus a capacitor. Yep, 100%. So inductive loads like the motors and transformers cause the current to lag the voltage due to the energy stored in the magnetic fields. When there's a change in current, the collapsing magnetic fields induces a back EMF, which opposes the change in current. The lag creates a reactive power, which lowers our power factor. Cool. So why do we pay for apparent power and not just the true power? Yep. So basically, supply network must provide both the current for the true power, the work that's actually done, and the reactive power, which is the energy exchange. So even though reactive power does nothing, it increases the total current. So equipment must be rated for apparent power, and we need to pay for it. Cool. So how does adding a capacitor improve our power factor? So it reduces the overall reactance, but how? How does it do it?